Right now, a single modern rack of H100 GPUs is pulling enough power to basically run an entire neighborhood.
Oh, easily. Yeah.
And if the liquid coolant flowing through that rack stops for literally any reason, the silicon will generate enough heat to melt itself in roughly 45 seconds.
Yep. 45 seconds. It's wild.
Welcome to the deep dive.
Yeah.
You know, when you read all the endless headlines about artificial intelligence right now, there is this almost universal tendency to treat the cloud like, well, like magic.
Oh, completely. It's a very clean narrative.
Right. We picture algorithms just kind of floating in the ether, large language models materializing answers out of thin air. We talk about AI as this weightless, invisible, frictionless reality.
Yeah, the industry actually loves to frame AI entirely as a software story. Like it's just this triumph of pure data and logic and mathematics.
Just code.
Exactly, just code completely detached from the actual physical constraints of the real world. But I mean, the physical reality is fundamentally different.
It's heavy.
Oh, it's so heavy. When you walk onto the floor of a facility where these massive models are actually being trained, it is not a quiet, invisible process at all. It is a deafening industrial environment.
Heavy metal.
Heavy metal, high voltage electrical architecture, massive fluid dynamics. It's a place where, millions of gallons of water and just megawatts of electricity are being consumed to do the heavy lifting for those floating algorithms.
Which perfectly brings us to our mission for today. We are pulling back the curtain on the heavy metal reality of AI.
Let's do it.
We're diving into a highly detailed set of architectural documents and operational blueprints. These are provided by Supermicro and Ventas.
Right, and their focus is on what they're calling converged infrastructure for modern AI data centers.
Yeah, converged infrastructure. And our goal for this deep dive is to basically demystify how extreme density computing has just completely shattered the traditional rules of data center management.
Shatter is the right word.
We are going to explore the intense engineering race to build a new, deeply unified ecosystem that prevents these multi-million-dollar AI hubs from going dark or, physically destroying themselves.
Right. And to really grasp the gravity of what Supermicro and Ventas are proposing here, we have to start by kind of diagnosing the failure of the current model.
The old way.
Yeah, the old way, because you cannot appreciate the elegance of a converged solution until you understand why the old way of managing infrastructure is actively breaking under the weight of high-performance computing, or HPC, and, well, AI workloads.
So paint that picture for us.
Yeah.
What did the old way look like?
So for the past 2 decades, traditional enterprise computing was built around a highly siloed, compartmentalized operational model. Data center operators were managing standard, relatively low-density racks, and they used these highly fragmented software tools to do it.
The classic legacy trap.
Right, exactly.
You had your compute architecture, your network topology, your storage arrays, and each of those existed in its own little operational bubble.
Total bubbles. You might have one software platform just for monitoring your servers, right? Then a completely different web interface for your power distribution units.
The PDUs.
Right, the PDUs. And then a completely separate facility-level building management system for the air conditioning.
And for a long time, that was fine, right?
It was sufficient, yeah. A standard enterprise server running, say, basic web applications or database queries, it might draw maybe 5 to 10 kilowatts per rack.
Which sounds like a lot, but not compared to today.
No, not at all. At that density, the power and cooling variables move relatively slowly. The room heats up gradually.
Right.
But the transition to dense GPU clusters has totally upended the physics of the room. Today, an operator isn't just looking at a few dozen CPUs. They're managing racks that draw 80, 100, or even 120 kilowatts.
120 kilowatts for one rack. That's insane.
It is. They are dealing with in-rack coolant distribution units, really complex facility-level thermal systems, diverse power feeds. Yet, many operators are still attempting to manage this new hyper-dense reality using those same disparate, fragmented legacy tools.
It makes me think of flying a modern commercial jet, but with a completely broken cockpit design.
Oh, that's a good way to look at it.
Right. Imagine trying to pilot a massive aircraft where the altimeter, the fuel gauge, and the engine temperature dials aren't just on different dashboards, they're physically located in different parts of the airplane.
Right, like totally spread out.
Exactly. The altimeter is up in first class, the fuel gauge is mounted on some bulkhead back in economy, and the engine temperature dial is locked in one of the bathrooms.
That sounds stressful.
You're running back and forth, right? Trying to piece together a holistic view of whether the plane is flying straight.
Yeah.
By the time you check the altitude, your fuel reading is entirely out of context.
It's a completely chaotic way to operate, and that analogy captures the latency of human decision-making perfectly.
Yeah.
But the source material actually introduces an additional layer of friction that makes your airplane scenario even worse.
How could it be worse?
Well, it's called vendor integration complexity.
Ah,
Imagine those fragmented dials in your airplane were all manufactured by different companies who actively refuse to communicate using the same language.
that's the reality of a modern data center, isn't it?
It really is. You have power infrastructure from vendor A, cooling manifolds from vendor B, and the compute itself from vendor C.
Okay, now, anyone who has worked in enterprise IT is going to push back here and point out that we have industry-standard protocols designed specifically to solve this exact problem.
Sure, people always bring that up.
Right. The documents explicitly mention standards like Redfish, SNMP, Modbus, Open APIs. Shouldn't these standardized protocols act as basically the universal translator between all these different vendors?
I mean, in theory, yes, absolutely.
But in practice,
In practice, the implementation of those standards is notoriously inconsistent.
give me an example.
Take SNMP, for example, Simple Network Management Protocol.
Okay.
It has been around forever, but it relies on something called MIBs, or Management Information Bases. Yeah. Every vendor creates their own custom extensions for their specific hardware.
So they tweak it.
Exactly. So if vendor A releases a firmware update for their power unit, they might change the data structure of their MIB.
Oh, I see where this is going.
Right. Suddenly that custom integration script that the data center operator wrote, the one pulling that data into their central dashboard, it just completely breaks.
Because the language changed slightly.
Yep. And then you look at Modbus, which is even older. It was originally designed for industrial programmable logic controllers.
Like factory equipment.
Yeah, factories. It's a serial communication protocol that relies on reading specific memory registers. It is highly rigid, difficult to scale in a dynamic IT environment, and it requires this really painful manual mapping of data points.
So even with a modern RESTful API standard like Redfish, you are still totally at the mercy of how well the original equipment manufacturer, the OEM, actually wrote their API endpoints.
Precisely that. Real-world compatibility is dictated by tested device support, firmware version variances, and just the sheer lack of deep cooperation between competing OEMs.
They don't want to play nice.
They really don't. And the consequence of this vendor integration nightmare is what the source material identifies as the most critical vulnerability in the modern AI data center, the lack of a single end-to-end view.
Oh,
When data center personnel can only observe individual components in a vacuum, they lose the ability to correlate intersecting telemetry.
right. Because in a high-density AI environment, literally nothing happens in a vacuum.
Yeah.
A spike in GPU utilization instantly changes the power draw,
Instantaneously.
which instantly changes the thermal load.
Exactly. And if you are relying on fragmented systems, you cannot see that causality.
You're blind to the connections. You are.
You might see a sudden surge in rack power consumption on one dashboard, but because you have to literally log into a completely separate application to view the telemetry from your coolant distribution unit,
Let alone calling the facility manager to check the building's overall power usage effectiveness.
right, you are fundamentally operating in the dark. You are reacting to secondary symptoms rather than managing the holistic system.
And what are the consequences of that, according to the documents?
The document outlines severe operational consequences. Massive workflow delays due to manual handoffs between siloed teams.
Because they have to call each other.
Yeah. Delayed deployments of new AI clusters because capacity planning is basically a guessing game, and a significantly higher risk of catastrophic outages.
You can't see the domino effect.
Exactly.
You can't see that a localized drop in coolant pressure on Tuesday is the direct cause of a GPU thermal throttling event on Wednesday, because those two data points live on completely different screens and are monitored by completely different teams.
That's it, exactly. The legacy model is structurally incapable of managing the speed and density of AI.
It's too slow.
Way too slow. And because that old system of fragmented dashboards has reached its absolute limit, the architectural philosophy of the data center had to be completely reimagined.
So what's the solution?
Supermicro and Benthaus argue that you can no longer just manage servers. You have to manage an interconnected ecosystem.
Okay.
The modern operational model now mandates a unified three-domain architecture.
3 domains. Let's break down the anatomy of these three connected domains, because understanding how they intersect is really the key to understanding the rest of this whole infrastructure puzzle.
For sure.
We'll start with the first domain, which is what we traditionally focus on, right? Systems.
Right. The systems domain encompasses the compute and network infrastructure located inside the rack itself.
The hardware.
The hardware. We are talking about the central processing units, the massive GPU clusters, the high-speed storage arrays, the network switches, the firmware states, and the overall topology of the hardware.
Basically the brain doing the actual mathematical heavy lifting for the AI models.
Exactly. But the source material makes a very specific point to differentiate these modern AI racks from the standard server racks of a decade ago.
How so?
The density and the interconnectivity have scaled just exponentially.
Okay.
You are no longer managing a simple 1U pizza box server running a single web application. You are managing dense compute zones where 8 or more massive GPUs are tightly coupled together.
Using those proprietary interconnects, right? Like NVLink.
Yes, exactly like NVLink. They are operating as a single massive parallel processing unit to train a large language model.
So they act as one organism.
Right. The internal dependencies are vastly more complex, which means the power requirements are astronomical.
Which naturally brings us to the second domain,
Yeah.
power.
Yes.
The digestive system of the data center, if you will.
I like that, yes. The power domain covers the entire electrical life cycle, how energy is delivered, measured, controlled, and protected.
From the grid down to the server.
Exactly. Moving from the macro facility level all the way down to the individual server outlet.
What?
In the past, tracking power was mostly, a monthly accounting exercise. You just did it to pay the utility bill.
Right. Check in meter.
Yeah. But with AI racks drawing over 100 kilowatts each, having granular millisecond-level visibility into your power infrastructure is a critical operational necessity.
Because things can trip so fast.
Exactly. You are monitoring phase balancing, load capacities, and power quality across an incredibly stressed electrical grid.
Which logically forces the third domain into existence.
Yes, it does.
Because if you are cramming all of this dense compute into the systems domain, and you are pumping astronomical voltages through the power domain to feed it, the laws of physics dictate that all that energy has to go somewhere.
Energy doesn't just disappear.
Right. The heat generation must be catastrophic.
It really is. And that introduces the third domain, cooling.
The thermal infrastructure.
Right. It encompasses the liquid cooling loops, the coolant distribution units, the CDUs, the flow rates, the pressures, the supply and return temperatures, the leak detection sensors, and even the macro-level facility cooling towers outside.
Okay, I want to pause here and look at this logically for a second.
Sure.
Hasn't cooling always been a massive part of running a data center?
Of course.
If I think about traditional data centers, the defining characteristic is usually the deafening roar of massive air conditioning units. The Kissir IC units pushing freezing air up through raised floors.
Right, exactly.
So why does the source material treat thermal management as this revolutionary new interconnected domain rather than just standard facility maintenance?
That is a great question. It fundamentally comes down to the physics of heat transfer and the limits of air as a cooling medium.
Air has limits.
Massive limits. Air is actually a terrible conductor of heat. Yeah, it has very low thermal mass. In a traditional data center, cooling was essentially treated as a building services concern. You chilled the air in the room, blew it across the servers, and the ambient environment kept the hardware within safe operating margins.
Like air conditioning your house.
Yup, basically, yeah. But as rack power densities pushed past 20, 30, and now 100 kilowatts, the thermal resistance of air became an insurmountable bottleneck.
Meaning you literally can't blow enough air fast enough.
Exactly. You simply cannot move enough cold air fast enough over a densely packed GPU cluster to extract the heat it is generating.
So you have to bring a better conductor directly to the source of the heat.
Right.
You have to use liquid.
Yes. Liquid cooling is orders of magnitude more efficient at capturing and moving heat.
But I imagine that changes the game entirely.
Oh, it changes everything. Moving from ambient air cooling to direct-to-chip liquid cooling changes the entire risk profile of the facility.
How so?
Well, cooling is no longer just about maintaining a comfortable ambient environment for uptime. It is now a minute-by-minute functional requirement for physical survival of the hardware.
The actual survival.
Yes. If a traditional air-cooled server loses its room air conditioning, the ambient temperature rises slowly. You have hours to react, shut things down, or migrate workloads.
Because the room takes time to warm up.
Exactly. But if a highly dense, liquid-cooled AI rack loses flow in its microchannels, the thermal runaway is almost instantaneous.
How instantaneous are we talking?
The silicon will overheat and critically fail in a matter of seconds. Like we said earlier, 45 seconds, and it's melting.
Wow. So it shifts from being an environmental factor to being active life support.
That's the perfect term for it, active life support.
If the circulatory system, the cooling domain fails, the systems domain dies before a human being can even register the alarm on a dashboard.
Exactly. Which is why these three domains can no longer operate in siloed isolation. They are deeply, intrinsically reliant on each other.
They have to talk.
They must talk. And to manage an ecosystem where power, thermal loads, and compute are shifting in milliseconds, you need a single, highly intelligent control plane to coordinate them all.
And according to the architecture outlined by Supermicro and Ventas, that centralized brain is a software platform called SuperCloud Composer, or SCC.
Yes, SuperCloud Composer. It is presented as an open, distributed infrastructure management platform.
Right.
And the most fascinating architectural decision here is its foundation. SCC utilizes a scalable Kubernetes control plane to unify all these disparate physical domains into one streamlined operational reality.
I find this absolutely fascinating from a software engineering perspective.
It really is.
When you hear the word Kubernetes, you immediately think of cloud-native software development, right?
Corporate services.
Yeah, it's an orchestration system designed to manage virtual containers of code, spinning up microservices, balancing web traffic, ensuring software applications are resilient.
Standard software stuff.
Exactly. But here, they are taking a Kubernetes control plane and applying it to heavy physical infrastructure.
Yes.
They are treating high-voltage power distribution units and industrial liquid cooling manifolds as if they were just software endpoints. Endpoints that can be declared, observed, scaled, and managed with a line of code.
It is a brilliant application of abstraction.
Tell me more about that.
By treating physical hardware as declarative state objects within a Kubernetes architecture, SCC essentially strips away the vendor complexity we talked about earlier.
So it solves the SNMP and Modbus problem.
Basically, yes. The software isn't just reading a static list of IP addresses. It provides a foundation to dynamically discover, monitor, observe, and manage the physical environment.
Dynamically.
Yeah, dynamically. When a new physical piece of hardware is plugged into the network, the Kubernetes control plane auto-discovers it, provisions it, and integrates its telemetry into the unified state of the data center.
Let's ground this in reality for a second. What does that abstraction actually look like in practice for an operator managing the power domain?
Okay, let's examine the SCC PDU console.
All right.
A modern power distribution unit is essentially a highly intelligent, network-connected power strip that routes electricity into the servers.
Like a super smart extension cord.
Basically, yeah. Because SCC is integrated at the protocol level, it isn't just pulling an overall voltage reading for the whole strip.
Okay.
It actively collects detailed physical asset information, real-time sensor data, the electrical phase balancing, and the minute-by-minute energy consumption at the individual outlet level.
So it knows the exact electrical draw of a specific GPU node on a specific rack at any given millisecond.
Yes, down to the millisecond. And it visualizes this telemetry contextually.
What do you mean by contextually?
Well, the documents showcase this hierarchical rack view. It's not just a flat spreadsheet of Modbus registers anymore.
Thank goodness.
Right. The operator can actually pull up front and rear visual representations of the physical rack on their screen.
Oh, like a 3D model.
Kind of, yeah. A physical mapping. They can see the exact component mapping, locate a specific PDU within a sprawling facility, monitor its live electrical telemetry, and crucially analyze its historical power data.
That historical context seems pretty vital.
It is huge.
It changes the operational question from, is this server currently on, to how has the power consumption profile of this specific training cluster shifted over the last 3 weeks of this AI run?
Exactly. The historical analytics allow for predictive capacity planning. You can see trends before they become problems.
That's powerful.
It is. But SCC also enables active remote intervention. The PDU console gives operators the ability to execute remote outlet power controls.
So they can turn things off.
Yeah, they can cycle the power on a specific outlet directly from that unified interface.
So if you are an infrastructure engineer sitting in a control room in, say, Chicago,
Okay.
And a critical edge compute node in Frankfurt locks up at the hardware level.
A frozen server.
Right. You don't have to submit a ticket for a remote hands technician in Germany to walk the data center floor and physically pull the power cable out of the wall.
Nope, not anymore.
You initiate the command through SCC in Chicago. The control plane communicates with the specific PDU in Frankfurt, drops the voltage to that single outlet, and forces a hard reboot, all in seconds.
All in seconds. The operational efficiency gained by that level of remote management is just immense, especially for highly distributed edge sites.
I can imagine.
It really tightens the loop between observation and remediation. But as we established earlier, power is only one side of the equation.
Right.
The most urgent physical threat in these high-density environments is the thermal runoff, the heat.
So how does this unified control plane manage the circulatory system, the cooling?
Let's follow the cooling chain.
Okay.
Because the SCC cooling infrastructure module doesn't just look at a basic thermometer in the room. It tracks the thermal journey from the micro level of the silicon all the way out to the macro level of the environment outside the building.
Where does that telemetry chain actually begin?
It begins inside the rack, directly at the interface of the compute.
Right at the chip.
Exactly. SCC continuously monitors the coolant distribution units, the CDUs. These can be integrated directly into the rack itself or placed in the row next to the racks.
Okay.
The telemetry they provide is incredibly granular. They monitor the supply temperature, that's the chilled liquid entering the server block,
Right.
and the return temperature, which is the heated liquid exiting the block after it has absorbed the thermal energy from the GPUs.
By measuring that delta, the difference between the supply and return temperatures, the software can calculate exactly how much heat the AI workload is generating in real time.
Spot on. It calculates the thermal load instantly.
Wow.
But temperature is really just the baseline. SCC is also pulling telemetry on the fluid dynamics within the loop.
Like how fast the water is moving.
Exactly. It monitors the volumetric flow rate of the coolant, the physical hydrostatic pressure inside the microchannels, the RPM and operational status of the circulating pumps, and the actuation status of the control valves.
That is a lot of data.
It is a complete real-time diagnostic of the entire fluid network. And of course, all of this is tied directly to the leak detection matrices.
Because the concept of pumping pressurized liquids directly over the top of unshielded high-voltage circuitry is inherently terrifying.
Oh, it's a nightmare scenario.
A leak isn't just a mess on the floor, it's a catastrophic electrical event.
Exactly. It is the ultimate disaster scenario, which is why leak detection telemetry is treated with the highest absolute priority within the control plane.
Makes sense.
But the rack-level CDUs are really just the first loop. SCC also integrates with supplemental cooling architectures,
Like what?
like rear door heat exchangers, which capture the ambient heat bleeding off the back of the rack, and sidecar cooling units.
So it's looking at air too.
Yes. It monitors air velocity and ambient pressure differentials right alongside the liquid telemetry. But the real power of the converged infrastructure is what happens when you zoom out from the rack and look at the facility level.
The macro view.
Yes, the macro view.
So when we step outside the data center floor, what is SEC actually looking at?
It integrates with the massive industrial facility cooling systems. We're talking the big cooling towers, the primary chiller loops, the external heat exchangers.
Great.
The software monitors the macro water temperatures, the variable frequency drives on the massive facility pumps, the water levels in the external basins, and highly specific metrics like water and fluid quality.
Okay, I have to push back on that specific detail.
Go for it.
Monitoring pump speeds and water temperatures makes total sense to me. But basin water levels, fluid quality.
Yeah.
Why on earth does a software engineer managing an AI workload need telemetry on the chemical quality of the water in a basin outside the building?
I know, sounds weird.
Are we running a data center or a municipal water treatment plant here?
It sounds like a totally minor facility maintenance triviality until you understand the microscopic tolerances of direct-to-chip liquid cooling.
Explain that to me.
So the cold plates that sit directly on top of modern GPUs, they rely on incredibly intricate microchannels to maximize the surface area for heat transfer.
To pull as much heat off the silicon as possible.
Exactly. And these channels can be fractions of a millimeter wide.
Oh, wow. That's small.
Tiny. So if the chemical quality of your facility water degrades, let's say the pH balance shifts, or the biocides fail and you get organic growth, or even if hard water introduces particulate matter, what do you think happens to the physical plumbing?
You get mineral scaling, you get a buildup of gunk inside the pipes.
You get scaling, galvanic corrosion in mixed metal loops, and particulate blockages.
Okay, I see.
Think about your house. A mineral blockage in a pipe means your shower pressure drops.
Right.
Right. Annoying, but whatever.
Great.
In an AI data center, a microscopic blockage in a GPU cold plate means the coolant flow stalls over a specific quadrant of the silicon.
Oh, no.
Yes. The heat cannot be evacuated, the localized temperature spikes violently, and that $3 million compute node destroys itself in seconds.
That makes the stakes incredibly real.
Totally real.
So a chemical imbalance in a cooling tower basin on Monday is the direct physical cause of a melted GPU cluster on Friday.
Exactly. And this illustrates perfectly why the fragmented legacy system fails so hard.
Because they aren't talking to each other.
Right. In the old model, the facility engineer monitoring the water basin chemistry outside is absolutely not communicating with the IT administrator deploying the Kubernetes pods for the AI training run inside.
They probably don't even know each other's names.
Exactly. But with a unified platform like SCC, the system correlates the entire chain from end to end.
So it can see the big picture.
It can detect a degradation in fluid quality at the facility level, correlate it with a microscopic drop in flow pressure at the rack level inside, and identify that a catastrophic thermal event is imminent, days before the temperature actually spikes.
Which brings us to the most critical function of this entire architecture, I think.
Autonomy.
Right, because having the smartest, most correlated dashboard in the world is completely useless if a human being still has to click the mouse to save the system.
Humans are too slow.
Right. If thermal runaway destroys a rack in 45 seconds, human reaction time is irrelevant. The software basically must move from passive telemetry to autonomous action.
And that transition from observation to automated remediation is the defining characteristic of a converged infrastructure.
How does it do it?
The Supermicro document outlines this through a highly detailed telemetry trigger event action matrix.
A matrix?
Yeah, it defines exactly how the software utilizes its unified view of the system's power and cooling domains to protect the data center autonomously.
Let's dive deep into this event action matrix. We'll start with the physical threats we were just discussing. What actually happens when the system detects a leak?
So if the telemetry trigger is leak detection, the autonomous action is multi-tiered. First, it triggers an immediate critical alarm and escalates a priority notification to the operations team.
Standard stuff.
Right. But crucially, because it is natively integrated with the system's domain, it instantly initiates workload protection protocols.
What does that mean?
It means it can begin gracefully draining the AI workloads off that specific rack and routing them to safe nodes elsewhere in the facility. And it does this before the localized power is automatically severed to prevent an electrical fire.
Wow, so it saves the data before it kills the power.
Exactly.
What about mechanical degradation? Let's say one of the in-rack pumps just starts to fail.
Okay, if the trigger is a pump or valve fault, the system generates a maintenance alert and automatically kicks off a service workflow,
Meaning?
dispatching a technician with the exact component data.
Nice.
But the intelligence goes far beyond just binary failure states. Consider the trigger, low flow rate, or pressure issue.
The blockage scenario we talked about.
Right. The software doesn't wait for the temperature to rise. The matrix specifically notes that this trigger identifies a cooling degradation event before thermal failure occurs.
That predictive capability changes everything.
It really does.
It sees the physical pressure dropping in the manifold, and because it understands the thermal load being generated by the GPUs, it basically mathematically deduces that a temperature spike is guaranteed to happen in the near future.
Even if the current thermals are perfectly green,
Wow.
it acts on physics, not just symptoms. And the same proactive logic is applied to the power domain, too.
Give me a power example.
If the telemetry indicates a PDU overload risk, the system doesn't wait for a physical circuit breaker to trip and take down the entire row.
Because that would be disastrous.
Totally. Instead, it fires off webhooks and syslog alerts to external automation tools to gracefully shed non-critical loads.
So it turns off the unimportant stuff to save the critical stuff.
Right. And if there is an outlet-level high power draw, the system isolates the anomaly down to the specific server and flags the abnormal consumption for immediate review, which prevents localized brownouts.
But the most sophisticated response detailed in this matrix, the real holy grail of converged infrastructure, from what I read, is what they refer to as GPU load automation.
Yes, GPU load automation is where the true ultimate convergence of facilities and compute really happens.
How does that work?
Well, the trigger for this action might be an electrical phase or load imbalance, a creeping cooling temperature breach, or even just a calculated scenario indicating reduced power cooling headroom across the facility.
Okay, so the building is stressed.
Right. The autonomous action is that the software directly interfaces with the job schedulers, like Slurm or Kubernetes schedulers, to dynamically shift, throttle, or pause GPU workloads based on the available physical capacity.
Okay, I have to challenge the logic of this from the perspective of the end user.
Sure, let's hear it.
If I am a data scientist and I have secured the massive budget required to kick off a highly distributed large language model training run across 1,000 GPUs, my primary concern is speed and synchronization. Right?
Right.
If a cooling pump starts acting erratically, and this infrastructure software decides to unilaterally throttle the clock speeds on a subset of my GPUs just to reduce the thermal load, doesn't that introduce massive latency cascades?
It definitely can, yes.
Doesn't throttling one node ruin the synchronization of the entire distributed training run and basically infuriate the client who is paying millions for maximum performance?
You are pointing out a very real friction point between infrastructure operations and data science. It is a huge debate right now.
I bet.
But it comes down to the grim reality of service-level agreements, or SLAs, and just the strict physical limits of the hardware. The document acknowledges this as a necessary, intelligent trade-off.
A trade-off.
Yeah.
Yeah.
Yes, dynamically throttling the p-states of a GPU will introduce latency. No one likes that. But consider the alternative in a legacy system.
The alternative being it crashes.
Right. If the infrastructure cannot throttle the workload, the degraded pump fails to clear the heat, the cold plate temperature exceeds critical thresholds, and the hardware undergoes a sudden, ungraceful thermal shutdown.
The node physically crashes.
It crashes hard. And a hardware crash during a distributed training run doesn't just cause a little latency. It can corrupt the model weights, destroy days of computational progress, and require the entire job to be restarted from the last checkpoint.
Oh, wow. So you lose all that time and money anyway.
Exactly.
Mm.
Throttling the workload is a temporary degradation of performance to ensure the physical survival of the cluster.
It's self-preservation.
Yes. The advanced schedulers communicate with SCC to implement intelligent checkpointing and micro-batch size adjustments, allowing the cluster to balance performance with the actual physical realities of the facility in real time. It protects the hardware, which ultimately protects the integrity of the workload.
So an intentional managed delay is always preferable to a catastrophic meltdown.
100%.
It's analogous to the engine management system in a modern car, actually.
Oh, how so?
Well, if the coolant temperature spikes because you are towing a heavy load up a mountain, the car's ECU will intentionally pull timing and reduce engine power.
Right.
It forces you to limp to the top of the hill slowly, rather than letting you keep the accelerator pinned until the engine block physically warps and cracks.
That is an excellent analogy, yes. It is an autonomous self-preservation mechanism that operates at speeds human operators literally cannot match.
Right.
And once you have built a system capable of solving those immediate existential threats of heat and power, you actually unlock the ability to optimize the economics of the entire operation.
Economics. Because the sheer cost of running these facilities is staggering, isn't it?
Yeah.
We're talking about utility bills in the tens of millions of dollars.
The financial burn rate of an AI data center is phenomenal. It's almost hard to comprehend, which is why the later sections of the Converged Infrastructure document focus really heavily on real-time efficiency metrics and economic optimization. The baseline metric for this is PUE, or power usage effectiveness.
For those listeners familiar with data center metrics, PUE is the classic ratio comparing the total amount of energy coming into the facility versus the amount of energy actually being consumed by the computing equipment.
Correct.
A perfect ratio of 1.0 means every single watt is going into the servers, and absolutely 0 watts are being wasted on overhead like cooling and lighting.
Exactly. But historically, data centers calculated their PUE retroactively.
After the fact.
Yeah. They looked at the monthly utility bill, looked at the server power draw over that month, and figured out a rough average.
Which is pretty useless in the moment.
Exactly. Legacy PUE calculations are notoriously misleading when applied to highly dynamic, liquid-cooled AI clusters. By continuously aggregating the telemetry from the system's power and cooling domains, SCC provides a live, real-time PUE metric.
So you see it second by second.
Right. It shows the true efficiency of the data center at any given second. But where it transitions from mere monitoring to active financial management is through integration with wholesale energy markets.
The energy markets.
Yes, specifically utilizing LMP.
Okay, how does LNP factor into this?
Well, LMP stands for locational marginal pricing.
Okay.
It is the mechanism by which wholesale electricity prices are calculated based on the actual real-time cost to deliver power to a specific node on the electrical grid.
So it changes based on location and time.
Exactly. The price of electricity is not static. It fluctuates wildly based on regional supply, consumer demand, and physical transmission congestion on the grid.
It's essentially real-time surge pricing for electricity.
That's a perfect way to describe it.
Like if it's a sweltering August afternoon in Texas and everyone in the state turns on their residential air conditioning, the demand on the ERCOT grid skyrockets and the cost per megawatt hour spikes astronomically.
Precisely. And a deeply converged infrastructure allows the data center to perform real-time energy price response via LMP.
Meaning what exactly?
SCC can actually ingest those live wholesale pricing API feeds from the grid. When it sees the price of grid power spike at, say, 4:00 p.m., the software can autonomously react.
By doing what?
It can interface with the job schedulers to pause non-urgent, highly power-intensive AI training jobs, shedding load from the grid until the price drops back down in the evening.
Wait. So the infrastructure software is essentially acting like a high-frequency Wall Street day trader.
Exactly.
But instead of buying and selling equities, it is trading megawatts.
Yes, trading megawatts.
It is constantly adjusting the computational output of these massive GPU clusters to optimize against the real-time financial fluctuations of the global energy market.
It turns the data center into a highly elastic, grid-interactive asset.
That is wild.
If power is cheap, it accelerates the workloads to maximum capacity. If power is expensive, or if the grid operator sends a demand response signal to prevent a blackout, the data center instantly sheds load by throttling compute.
So it's saving money and saving the grid.
Exactly. And this economic elasticity brings us directly to the future view outlined at the very end of the source documents.
The future horizon.
Yeah. The ultimate evolution of this architecture isn't just monitoring or reacting, it is full orchestration.
Orchestration implies acting as the conductor for a much larger, more complex symphony. What exactly are they orchestrating?
They are looking toward energy source orchestration. The AI data centers of the near future will not rely on a single static connection to a municipal utility grid.
They won't just plug into the wall.
No. They will manage a highly complex, localized portfolio of power generation and storage.
Like what?
The document points specifically to orchestrating a mix of power from the traditional grid, massive battery energy storage systems, or BESS hydrogen fuel cells, localized solar microgrids, traditional backup generators, and eventually advanced baseload technologies like small modular reactors.
Small modular reactors, SMRs. We are talking about localized, dedicated nuclear fission reactors built on-site specifically to feed the power demands of a single AI data center.
I know it sounds like science fiction, but from an engineering and capacity standpoint, localized nuclear power is increasingly viewed as the only viable path forward.
To meet the demand.
Right, to meet the projected gigawatt-scale energy demands of the next generation of artificial intelligence without catastrophically overloading the existing public grid.
And the Converged software platform will be tasked with orchestrating all of this.
Yes. If the on-site solar arrays are overproducing on a sunny afternoon, the software routes that cheap excess power to charge the BESS, the batteries.
Right.
When the sun goes down and grid pricing spikes, it seamlessly switches the data center's primary draw to those batteries, all while maintaining the baseload from the SMR.
And it's doing all of this while continuously running predictive maintenance algorithms. Right?
Oh, yes.
Using the microtelemetry from the cooling and power domains to basically identify hardware degradation before it impacts operations.
Exactly. When you connect all these pieces, the localized nuclear power, the real-time grid trading, the liquid cooling fluid dynamics, and the predictive workload throttling, it fundamentally redefines what a data center actually is.
It's not just a building full of computers anymore.
No, it transitions from being a passive, dumb consumer of electricity into an active, highly intelligent, dynamic participant in the global energy ecosystem.
It is a stunning evolution. We started this deep dive talking about the popular illusion of the cloud. You know, this idea that AI is just weightless code floating in the ether.
The magic.
Right. And we looked at how the legacy approach to infrastructure was this fragmented, chaotic mess with operators basically flying blind across a dozen different vendor dashboards, waiting for things to break.
They were entirely reactive, completely trapped by a lack of correlated data.
But the reality of modern AI requires something entirely different. We've explored a physical architecture that behaves almost like a biological organism.
Very much so.
The massive compute clusters act as the nervous system. The high-voltage power distribution serves as the digestive tract. The intricate liquid cooling loops function as a highly pressurized circulatory system.
And sitting above all of it, acting as the brain.
Is a unified Kubernetes control plane. Software that constantly monitors, correlates, and autonomously manipulates the physical world to keep the entire organism alive, efficient, and financially viable.
It is a profound engineering achievement. And when you understand the scale and complexity of this converged infrastructure, I think it completely changes how you view the technology we interact with every day.
Oh, absolutely.
The next time you open an app and casually ask a large language model a complex question or prompt an AI to generate a high-resolution image, remember that you are not just executing code.
You are initiating a massive physical event.
Yes. To deliver that answer to your phone in a matter of seconds, an incredibly complex symphony of fluid dynamics, phase load electrical balancing, and localized energy price trading had to execute flawlessly.
Thousands of miles away.
Thousands of miles away, all just to keep a multi-million-dollar rack of silicon from melting itself into slag.
It really grounds the magic of AI in a very heavy, very tangible reality.
It definitely does.
But it also leaves me with a lingering, slightly provocative thought to chew on as we wrap up today.
Let's hear it.
We have spent this entire deep dive discussing how this deeply integrated infrastructure software dynamically manages, throttles, and protects the AI workloads based on the real-time constraints of physics and economics.
Right.
It is a highly intelligent system managing the AI. But given the exponential rate at which artificial intelligence models are advancing, how long is it going to be until the AI itself is tasked with managing its own physical infrastructure?
That is a fascinating extrapolation. It touches on the ultimate horizon of autonomous operations.
Right. I mean, if the AI can understand complex code and optimize logistics, could the next generation of models be given direct control over their own Kubernetes control plane?
It's entirely possible.
Could the AI rewrite the code that governs its own fluid dynamics, maybe intentionally overriding the cooling valves to overclock its own processors when it needs to solve a particularly difficult problem?
That's a slightly terrifying thought.
It feels like we are rapidly approaching a threshold where the machine takes over the controls of its own physical life support system, basically optimizing its own environment to think faster.
Wow.
Just something to mull over the next time you ask an AI to summarize an email for you. Thanks for joining us on this deep dive. We'll catch you next time.